Welcome, this is Professor Ridge, and today's lesson is on 1.3, Radicals and Rational Exponents. And today's learning objectives, we will start with number 1, evaluate square roots. Right, the principal square root of a is the non-negative number that, when multiplied by itself, equals a. It is written as a radical expression with a symbol called a radical over the term called the radicand. So this is read as the square root of a. Okay, so again, this is the radical sign. Radical or radical sign. The number that's inside the a, that's called the radicand. So the number inside the radical sign's the radical, or the radicand. Right, radicand. The symbol, that's the radical sign, or just the radical. And then this radical expression is interpreted as the principal square root of a. Okay, a misconception about square roots, as I hear a lot of times people say, all right, the square root of 25 is plus or minus 5. And that is incorrect, because this, by definition, up here you can see, this is not the square root, it's the principal square root. And the principal square root is the non-negative number that if you square, so 5 squared is 25, and negative 5 squared is also 25. So yes, negative 5 squared is 25, but this symbol is the principal square root, so it's the non-negative square. It's the non-negative number that when you square it, you get 25, so that's just the 5. So it's just 5. Okay, so that's a common mistake. Now, if I was asking you to solve this equation, what squared is 25? This will have two solutions, plus or minus 5, right? And this is shorthand, if you don't know, for positive 5 or negative 5. Okay, so this symbol plus or minus is shorthand to show the two roots of this equation, which is a different question than saying what's the square root, or I should say principal square root, right? We get lazy and we drop that word principal. Okay, so it's principal square root. Okay, looking at example 1a, what is the principal square root of 100? So again, we typically get lazy and we just say square root of 100, but remember, when it's written this way, it's just the non-negative square root of 100. So what squared is 100? So that should be an easy one for you to know. 10 squared is 100, so this is going to be 10. And then for B here, now you got to think of order operations. The radical sign is a grouping symbol. So we're going to do inside the group, this grouping symbol first, get an answer, and then we can square root it. So the square root of 16 is 4. What squared is 16? Right? What squared is 16? So you see that's 4 squared is 16. So the square root of 16 is 4. And now we're going to ask the same thing. What squared is 4? That'd be 2. And of course you can punch this in your calculator and get that answer if you didn't know that 2 squared was 4. Alright, again, what I was just saying a minute ago is that you can think of radicals as, the radical sign is a grouping symbol, and you have the radicand, the number inside. You got to make that one number first. So we simplify. 25 plus 144 is 169. And then what squared is 169? Well, that's 13. And then on this one, okay, you got to simplify each of these radical expressions first and then subtract them. So in order operations, radicals are like exponents basically, and we'll probably talk about, yeah, we're going to talk about it in a couple examples further down, how you can view a square root as an exponent. Okay, so square root of 49 is, what squared is 49? Well, that's 7. Square root of 81 is 9, because 9 squared is 81. And then 7 minus 9 is negative 2. So remember, when you're subtracting, if it's, you want to think of it like this. So if you have a positive number and a negative number, the rules are for adding positive and negative numbers. If the signs are the same, you add the numbers, keep the sign. If the signs are different, you subtract the numbers. So 9 minus 7 is 2, and you take the sign of the larger number. Okay, on to the next learning objective. Use the product rule to simplify square roots. The product rule for simplifying square roots. So if a and b are non-negative, the square root of the product AB is equal to the product of the square roots of a and b. Okay, so here it's written in symbols. So again, this is the product of AB, then the square root of that. So the square root of the product AB equals the square root of A times the square root of B. So you can split this product up into the square root of each of the factors. All right, so the book gives this detail of how to given a square root, let's see, given a square root radical expression, use the product rule to simplify it. So your first steps, you're going to factor any perfect squares from the radicand. Write the radical expression as a product of radical expressions, basically using the rule above, and then you simplify it. So let's do a simple one. So let's say you had like a square root of, I don't know, let's see, how about 28? So square root of 28. So the idea then is you're supposed to think of the biggest perfect square factor of 28. So you think of all the factors of 28, and you can think of it, it's 4 times 7. So I can split it up into 4 times 7. 4 is a perfect square, meaning that it's 2 squared. And then using the rule above, I can rewrite this as square root of 4 times square root of 7, and then simplify. Square root of 4 is just simply 2. And again, remember, it's the principal square root. So it would be 2 times square root of 7. So it's 2 square root of 7 would be the simplified form. Now I do it a little differently, and I like to have my students factor everything. So if you're not really good at factoring, you can use a calculator with this, but it's not going to give, it'll give you a decimal number. So the way you would do it to get this the simplified radical form is you want to factor, so just whatever comes to your head. And again, I do a factor tree, so 28 is 2 times 14, or you could have done 4 times 7, and then 2 times. And I factor it all the way down until I get just prime factors. So that's going to be, and then you take the ends, 2 times 2 times 7. Now when I do square roots, I'm looking for perfect squares. So remember, 2 squared is the same thing as 2 times 2. Okay, so this is 2 squared. That's a perfect square. That's 4, right? So, but what I do is I just leave it in this factor form, and I kind of think of 2 factors on the inside make 1 factor of that factor on the outside. So the 2 2's on the inside become 1 2 on the outside. So that's the way I like to have my students do it. Let's look at example 2, and let's do it the way that I just described, the way I like to have my students do. So I'm going to use my factor tree, 300. Anything that ends in a 0, I can factor that out as a 10. So I'm going to take the 1 0, that'd be 10, and then 30. What's left over. And then 10 is 2 times 5. Those are prime numbers, so that's done. 30 is, I can do 3 times 10 or 5 times 6, whatever pops in your head. And then 5 is a prime number, right? Prime number, again, is any number that the only factors are 1 in itself. So you can't break this up into 2 times 3, right? Or 2 times something. It can only be 1 and 5. That's the only factors of 5. 6, you got 1 times 6 and 2 times 3, so that's not prime. So I'm going to split it up into 2 times 3. 2 is a prime number. 3 is a prime number. So I'm going to have 2 2's. So for 300, so this is scratch work. So for 300, I'm going to rewrite it as square root of, I got 2 2's, right? 2 2's, 1 3. I like to put it in order. You don't have to. And then 2 5's. 2 5's. And remember, I'm looking for pairs. I'm looking for perfect squares. So that's the square root of 4, which is 2. That's the square root of 25, which is 5. So 2 2's inside, make 1 2 outside. 2 5's inside, make 1 5 outside. And then I'm left with the 3 on the inside. And then I simplify this, so 2 times 5. So you can only multiply the stuff that's on the outside and the stuff that's on the inside separately, right? So 2 times 5 is 10, and then square root of 3. So this would be my final answer here. And just to kind of show you, so on Desmos, right, if I did the square root of 300, see, remember, it's an irrational number because there'll be a non-repeating, non-terminating decimal. So 17.32, and it goes on forever. If I did 10 times the square root of 3, and you see you get the same answer. So this is what's considered simplified radical form. And this is, it's still a radical expression. They're equivalent to each other, but to be simplified, you have to have every perfect square factor of the radicand, and you have to factor it out and simplify it. All right, let's look at B now. So for this one, so 162, let me do my little factor tree for 162. So that's 2, and then 81, and then if you see a perfect square like 81, I know is 9 times 9. I don't have to break this down into 3 times 3. I mean, I can, but I can stop. The two 9's on the outside will make, on the inside will make 1 9 on the outside. So I can leave it as the 9 times 9, but I'm going to go ahead and multiply, have it all factored out, since I told you that's what I like you to do. But in reality, I would have left it as 9 times 9 and then pull the 9 out. And then with the variables, I'm going to do the same thing. So I got 5 A's, and I'll show you a shortcut for this in a minute. And I don't know if I'm going to have room. 4 B's. Okay, so let's see. I'm looking for pairs. So there's a 3. Another 3. Another set of 3 or pair of 3's. And then for A's, 1, 2. Then that A is left over. Then a B and a B. And then I'm left with a 2 and an A on the inside. So 3 times 3 is 9. A times A is A squared. B times B is B squared. Square root of 2A. And that's my final answer there. Now, once you understand this totally, right, you could save some steps. Here's the shortcut for doing powers. We're looking for pairs, right? So remember, so if I want to do a to the 5th, I'm going to do 5 divided by 2, which is 2 remainder 1. So think of it that way. You know, if I did the long division back in grade school, 2 goes in 5 twice. 2 times 2 is 4. Subtract remainder 1, and then I just write the remainder 1. So 2 remainder 1. This is going to be the power that comes out, the 2, and the remainder 1 is the 1a that was left on the inside. Okay? And then for b to the 4th, 4 divided by 2, 4 divided by 2 is 2. 4 divided by 2 is 2 remainder 0. So 2 pairs of the b's come out and there's no b's left on the inside. So this would be, so 5 divided by 2, because it's square root. 5 divided by 2 is 2. 4 divided by 2 is 2. And then when we did 5 divided by 2, it was 2 remainder 1. 1a was left on the inside. And now you wouldn't write the, like, to simplify it, I wouldn't write that 1. So let me see if I can erase just that 1. I don't know if I can. There. Okay. So it's you're going. So if I had something like x to the, let's try something like this, x to the 13th. I'm going to go 13 divided by 2 is 6. Remainder 1. So that simplifies like that. Okay. So if I did 13 divided by 2, that would be 6 remainder 1. So this is how many come out. So x to the 6th power, and then x to the 1st power on the inside. The remainder tells you got that one left. Example 3, using the product rule to simplify the product of multiple square roots. Simplify the radical expression. So we have square root of 12 times square root of 3. Now there's a couple ways I do these. This one, since the numbers are small, I would use the product rule to combine this into 1 first. So square root of 12 times 3, which is 36. And then that's easy to recognize. Well, that's 6 times 6. So I'm not going to factor it. I'm just going to write the answer, right? So it doesn't hurt to just, you know, if you're not sure, just type in your calculator, hit the square root of 36 button, and it should tell you 6. If the numbers were bigger, let's say that we had something like square root of 50 times square root of 75, what I would do is I would still put it together as one factor, and then I'm just going to factor everything. 50 is 5 times 10, and then I got 5 times 2, and then 75 is 3 times 25, and that's 5 times 5. So I got a 2, a 3, 1, 2, 3, 4 5s. So I have a 2, a 3, and then 4 5s. And then using my other trick, I'm looking for pairs. So 2 5s inside make 1 5 out. And I got another set of those. And then the 2 and the 3 are left inside. And of course, once you practice a little bit, you don't have to show every step, but there you go. So 5 times 5 is 25. 2 times 3 is 6. Okay. I could have multiplied this and wrote down the number and then factor it, but then it's basically whatever that number 50 times 75 is, that's the number up here. So I'm going to factor it all down and look at the factors, so I don't need to really care about what 50 times 75 is, right? I can punch that in my calculator if I wanted to, but then I got to factor it, so why bother? All right, the next learning objective, use the product rule to simplify. Oh, we just did that one. We're going to the next one. Use the quotient rule to simplify square roots. the quotient rule for simplifying square roots. The square root of the quotient, a over b, so that's the quotient of a and b, is equal to the quotient of the square roots of a and b. So it's the quotient of the square root of a and the square root of b. Okay, now we're not allowed to have 0 in the denominator fraction because anything divided by 0 is not a real number, or not, it's undefined basically, it's not a number. Okay, so given a radical expression, use the quotient rule to simplify it. Write the radical expression as the quotient of two radical expressions. Simplify the numerator and the denominator. Looking at example 4, using the quotient rule to simplify square roots, simplify the radical expression. Okay, so that first step said to write the radical expression as a quotient of the two radical expressions. So we're going to do the square root of the numerator, square root of the top, divided by square root of the bottom, and then simplify these separately if you can. So square root of 5 doesn't simplify. Square root of 36, well, that's 6. 6 times 6. 6 squared is 36. And then that's it. This is simplified. All right, looking at example 5, using quotient rule to simplify an expression with two square roots, simplify the radical expression. Okay, so a couple ways we can go about this. We can actually go backwards and put them back together. So if you can see that you have some common factors here that we can reduce, you can actually use the radical rule in reverse that we did here. So we can take the 2 and put it together as one fraction inside, and then simplify that fraction. So 234 x to the 11 y over 26 x to the 7 y. Now again, if I think about it as factoring, right? 234 is, let's see here, does 4 go in that? No. Well, let's just do 2. So we get 1, 1, 7. And then 1, 1, 7. 9 will come out of that. So we get 1, 3. Then 9 is 3 and 3. So we got 2 times 3 times 3 times 13. And then x to the 11. Y, and on the bottom 26 is 2 times 13, x to the 7 y. Okay, so then I cancel. I like to use red for my canceling. Okay, the 2's cancel, 13 cancels. Now this I'm going to use exponent rules. So 11 minus 7 is 4 on the top, and then these y's cancel. Okay, so that simplifies to, let's see, I have 3 times 3, 11 minus 7 is 4, and then there's nothing left on the bottom. Over 1, so I'm going to leave that alone. See, everything canceled on the bottom because we canceled the 7 x's with 7 of them on top, and we're left with 4 on top. Okay, so the 3 comes out, 2 3's inside, make 1 3 outside, and then we're going to do the exponent trick on this one. 4 divided by 2 is 2, remainder 0, so there's nothing left inside, and that's our final answer. Okay, so that's probably the way I would do it if I'm not using a calculator and just doing everything by hand. And on to the next learning objective, add and subtract square roots. All right, how to given a radical expression requiring addition or subtraction of square roots, simplify. Simplify each radical expression. So that's, you have to do that first. So for every radical expression, make sure it's simplified. And then you can add or subtract expressions with equal radicands. This is what we refer to as like radicals. So to be like radicals, kind of like terms, you have to have equal radicands. So if I had 5 square root of 3 and 7 square root of 3, those are considered like radical terms because they have equal radicand, the square root of 3 part, right? So we're just looking at that part. So looking at example 6, 5 square root of 12 plus 2 square root of 3. Square root of 12 is not simplified, so that's our first step. We want to simplify square root of 12. 12 is 4 times 3, and again 4 is 2 times 2. So we got 12 is 2 times 2 times 3. We have the 5 that's on the outside already. So these two 2's make 1 2 on the outside. You have the 5 that's already there, and then a 3 left over. And then 2 times 5 is 10. 10 square root 3. Okay, so 5 square root 12, you're doing my scratch work, that's going to be simplified to 10 square root of 3 plus 2 square root of 3. Now this is what I tell my students is think of it as like if I had, think of square root of 3, what if I called that a? So square root of 3 is a, so then I have 2a. So if I asked you, and I don't have to write that dot, so it's just 10a plus 2a. 10a plus 2a. How would you combine those like terms? Well, you're going to add the number parts. And what we're really doing is we're factoring out the a, because that's what's common to both of these terms, and you're doing the distributive property in reverse. So don't forget that. Typically we just do it and just, 10 plus 2 is 12 and it's 12a, and we forget where it really comes from, you know, all the rules that we established in the beginning of algebra. We just kind of gloss over it and forget that, you know, it's grounded in sound logic. Okay, so 10 plus 2 is 12. So it's the same idea. So again, think of the square root of 3 as like the a, so I'm factoring it out. And again, you don't show the step. This is just what you think in your head. So you're going to add the 10 plus 2, and you're going to leave the square root of 3 alone. So it's just going to be 12 square root of 3. And of course, you skip that step. You don't write it down. You just think it in your head. So I'm going to put like a little mark here. Right? You don't have to show that. This is what you think in your head. Example 7, subtracting square roots. Subtract 20 times the square root of 72, a to the third, b to the fourth, c, minus 14 times the square root of 8, a to the third, b to the fourth, c. And remember, this is the principal square root. We just get lazy. And some people even getting more lazy and would just say 20 root. So you'll hear that a lot of times. Instead of saying square root, you just say root. But technically, right, it's the principal square root. All right. So again, we're going to simplify each of these. So 72, let's just look at the 72 for a moment. 9 times 8. 8's 3 times 3. 4 times 2. 2 times 2. So you can see for square root of 72, I'm going to get a 2 come out, 3 come out, and a 2 gets left inside. So I have 20 times a 3 comes out, 2 comes out. Okay, I'm going to leave room for the a and the b. Well, I'll go ahead and write them down. C is going to stay inside. Okay, so I brought out a 3, brought out a 2 gets left inside. Now, 3 divided by 2, remember the rule for the exponents, we're doing square roots, so you divide by 2, and that's 1 remainder 1. So 1a comes out, 1a is left inside. And then for b, 4 divided by 2 is 2 remainder 0. So 2 come out, and none are left inside. And then we got the c, which is just 1. So 1 divided by 2 is 0, remainder 1. Okay, and I don't, typically I wouldn't write that. I wouldn't write this 1 right here. Okay, the next one, 14, and then 8, so scratch work. 8 is 4 times 2, 2, 2. So a 2 comes out, a 2 gets left inside. An A is going to come out, a B is going to come out. Okay, so again, for 8, we have a pair of 2's, so 2 2's inside, make 1 2 outside. Then you got the 2 that's left over. A cubed, it's just like we did here. 3 divided by 2 is 1 remainder 1. So 1 with 1a left inside. And then 4 divided by 2 is 2 with 0 left inside. And then the c is just to the first power, so it's left inside. And you can see the radicand parts are identical. So these are what we call like radicals. So let's clean this up here. 20 times 3 times 2 is what? 120? 120 ab squared, square root of 2ac, minus 14 times 2 is 28 ab squared, and then 2ac. And you can see these are like radicals, so I'm going to do 120 ab squared minus 28 ab squared. So these are have the same variable part, so I can just subtract the numbers. 120 divided 120 minus 28. So that would be what, 92? So 92 ab squared square root of 2ac. All right, now to the next learning objective, rationalize denominators. How to. Given an expression with a single square root radical term in the denominator, you rationalize the denominator. So step A, multiply the numerator and denominator by the radical in the denominator, and then simplify. All right, so let's look at example 8 here. So if we have 2 square root of 3 over 3 square root of 10, and notice we're going to multiply both the numerator and the denominator by whatever the radical term is in the denominator. Okay, so if we have 2 square root of 3 over 3 square root of 10, we're going to multiply square root of 10 over square root of 10. Now, the thing to point out here is, remember, anything divided by itself is 1, so we're multiplying this fraction by 1, and anything times 1, anything times 1 is itself. So we're not changing the value of this fraction, we're just going to make it look different. And so to be considered simplified form, you're not allowed to have a radical expression in the denominator of a fraction. So this process of what we call rationalizing the denominator. So the top's going to become 2 times the square root of, we're going to use the product rule here, and we can put those together, 3 times 10. And then on the bottom, we have 3 times the square root of 10 times 10, which is 100. Square root of 100 is 10, or the shortcut, the way that I like you to think of it. You got 2 10s inside, so that makes 1 10 outside. So 2 square root of 30. Then on the bottom, we're going to have 3 these two 10s become 110 on the outside, and there's nothing left on the inside. Oh, and then we can reduce here. 2 divides into 10, leaves you 5. So 3 times 5 is 15. So that would be our final answer for simplifying 2 square root of 3 over 3 square root of 10. How to, given an expression with a radical term and a constant in the denominator, rationalize the denominator. So you're going to find the conjugate of the denominator, and we'll talk about that in a second. And you're going to multiply the numerator and denominator by the conjugate. So again, you're multiplying by 1, so you don't change the value. And then you use the distributive property and simplify. All right, so these are a little more challenging. So a conjugate is if you have a whole number plus whatever times a square root, you're just going, the conjugate, you just change that middle sign. So the conjugate would be a minus b square root of c. So these are what we call conjugate pairs. Okay, so you just switch that middle sign. So you're going to leave the first one alone. If it's positive or negative, doesn't matter. If the middle one's positive, you make it negative. If the middle one's negative, you make it positive, right? So you switch it. Okay, so here we got 1 plus square root of 5. So our conjugate is going to be 1 minus square root of 5. So we're going to multiply the top and bottom by 1, minus square root of 5. 1 minus square root of 5. Okay, so again, this is 1. Anything divided by itself is 1. So we're not changing the value. We're just simplifying, making it look different. So on the top, we got to distribute. So 4 times 1 is 4. 4 times square root of 5 is 4 square root of 5. So since 4 is a whole number outside the square root, and then the 5's inside the square root, you can't multiply them together. You just write 4 times the square root of 5. And then typically we don't write that dot. All right, so now for the bottom, then we're going to FOIL this. Now, the trick with the with multiplying by conjugates is it follows this pattern of a difference of squares. So I don't know if you remember that from intermediate algebra or even beginning algebra. When you FOIL this, you get the a squared minus ab plus ab minus b squared, and then these two terms cancel out, and you get a squared minus b squared. And we call that a difference of two squares. So when we FOIL this, we're going to get 1 times 1 is 1. You got the minus square root of 5 plus square root of 5. Those cancel. And then we got the square root of 5 times the square root of 5 is just 5, right? Because square root of 5, square root of 5. One's plus, one's minus, so it'll be minus. But then this simplifies to, you got the two 5's on the inside. Square root of 25 is just 5. So it's 1 minus 5, and then we can simplify that even more. So on the bottom we get negative 4, and then 4 minus 4 square root of 5. Now notice we have this negative 4, and it divides into both. So we're not going to worry about the 5. We're going to look at the 4 on the outside, this 4, and this 4. And you notice you can divide all three of these things by 4, or you can kind of think you can split this up into two fractions and then reduce the fractions. So either way that you want to think of it. So 4 divided by negative 4 is negative 1. Negative 4 divided by negative 4 is plus 1, square root of 5. And then since we have the square root of 5, we don't need to write the 1 in front of it. That goes back to that idea that 1 times any number is itself. So 1 times square root of 5 is just square root of 5. So I don't need to write the 1 in front. And this would be my final answer here. And on to the last learning objective for this lesson, using rational roots. So this is what I was talking about earlier, where you can think of a square root as a exponent. No, I think the book made a mistake. I think this should have been use rational. This is what I was talking about. Exponents. I don't know why they said roots. Understanding nth roots. The principal nth root. If a is a real number with at least one nth root, then the principal nth root of a written as, and then you have the radical sign, you have this little in here, we call that the index. So this is the nth root of a, is the number with the same sign as a that when raised to the nth power equals a. The index of the radical is n. So n is the index. So you can think of it this way. So like if we said the square root of 25, we're saying what squared equals 25? What squared equals 25? So that's 5 squared. So this would be 5. Okay, so now if we do the cube root of 125, we're saying what cubed is 125? And that's 5 cubed is 125 because it's 5 times 5 times 5. So that's 5. If I did the fourth root of 625, we're saying what to the fourth power? What to the fourth power is 125. I mean 625, sorry. Which is 5, because 5 to the fourth power. All right? So that's called the index. So if there's nothing written here, it's square, which the index would be 2. So 3, 4, you can go 5, 6, 7, so on. Okay, so the fifth root of negative 32, you're saying what, and we're going to know it's going to be negative because negative to fifth power is negative. What, I'm going to put the negative there, what to the fifth power is negative 32? And so if you go 2, 4, 8, 16, 32, that's 2 to the fifth is 32. So negative 2 to the fifth power is negative 32. So this answer is negative 2. Now, I can kind of tie it to my factoring thing too. I can factor it out, and you can see you have 5 negative 2's in there. So 5 2's inside make 1 2 outside. You can think of it that way. All right, we have 4, and all the rules work the same as long as the indexes or the indices, that's plural for index, are the same. So this is going to be the fourth root of 4 times 1024, which is the fourth root of 4096. So 4 times 1024 is 4096. And then you punch this in a calculator and you'll get 8. Or you can factor it out and see that you get 8 when you're all done. Okay, C. So I'm going to split this up into the cube root of the top and the cube root of the bottom. We're going to leave that negative out front. So we got the cube root of 8x to the 6 over cube root of 125. And we already established cube root of 125 is 5. So that's the bottom. Oh, I forgot my negative. And then this one is 8 is 2 times 2 times 2. So 2 comes out. And then we're going to do the dividing trick. So if the index is 3, we're going to take the power divided by 3. 6 divided by 3 is 2, remainder 0. So we don't have anything left inside the radical sign. So it's just x squared. So negative 2x squared over 5. And that's my answer for that one. And then this last one, 48. So again, 48. So we got 8 fourth root of 3 minus fourth root of 48. So in scratch work, I'm going to see if I can simplify this. So 48 is 16 times 3, and 16 is, you're going to have, oh, this was supposed to be fourth root. 16, you're going to have 4 2's, so 2, 4, 8, 16, and then the 3 to get 48. So I have the perfect fourth power, so 4 2's on the inside make 1 2 on the outside. So the index tells you how many of a kind you need, right? So 2, if it's square root, you need a pair, you need 2 of them. Cube root, you would need 3 of a kind. Fourth root, you need 4 of a kind. Fifth root, you need 5 of a kind, so on. Okay, so this is fourth root, so 4 2's inside make 1 2 outside. Then you got the 3 left over. So this simplifies to 8 fourth root of 3 minus 2 fourth root of 3. And again, you can think of this portion, the radical portion, those are like terms, like radicals. So you can kind of think of that like a variable. 8a minus 2a would be, you do the 8 minus 2 is 6, and then you leave the radical part alone. So you get 6 fourth root of 3. And that will be our final answer right there. Okay, so rational exponents are another way to express principal nth roots. So the general form for converting between a radical expression and a radical symbol with a rational exponent. So this is what I was talking about. You can think of a square root as a exponent using this rule here. Okay, so if you have a to the fraction exponent m over n, so rational is another way to say fraction, right? Ratio. You're going to take the numerator of that exponent, the fraction exponent, and that's going to be the power, and the denominator is going to be the index. So this is, well, let's look at example 11 here. So we're going to determine the power by looking at the numerator. So the power is 2. And then the root, determine the root by looking at the denominator, the index of the root, I should say. So the index would be the denominator. So this is going to be cube root of 343. And then we have a choice. We can put the square outside like this or inside. It doesn't matter. It's the same thing. So I can do 343 squared, or I can put parentheses around it, put the square out there. Either way. All right, so as simple as that. So if I had a square root, so let's just do another example. If I had square root of 5, I can rewrite this as 5 to the 1/2 power. Okay? And you can, go on your calculator and do square root of 5 and get an answer, and then do 5 to the power 1/2 or 5 to the power 0.5, and you'll see they're the same answer. You get the same number. Example 12, writing radicals as rational exponents. Write 4 over the 7th root of a squared using a rational exponent. So we're going to go in the other direction. So we have 4 over the 7th root of a squared. So 4 over, now they're not telling us simplify this, just write it using a rational exponent. So we're going to have the number inside, the base of this would be the base of the rational exponent. The power is the numerator, and the index of the root is the denominator. So it's just 4 over a to the 2/7, and it's as simple as that. You just learn the rule of how to convert back and forth, and it's pretty straightforward.